Aviation is seen as one of the biggest contributors to global warming. Airbus and other startup companies like Aerospace are working on alternative engine and propulsion options for a more sustainable future in aviation, with the first 30-seat electric airliner being released in the next years. What are the exact reasons why aviation is considered to be one of the biggest polluters? How can we minimize our impact today with existing technology, and how big actually is the impact? My name is Flo. Welcome to Fordeck. I'm currently working on my aircraft transport pilot license while looking forward to a long, fulfilling career in aviation as a pilot. I'm doing so while also seeing the devastating impact CO2 could have on our environment. That we humans are somewhat responsible for the big spike in average global temperatures over the last 100 years is almost certainly the case. The question is, how big is the actual impact? And today my big question is, how big is the actual impact caused by the aviation industry? During our theory training, we did not once talk about the environmental impact of aircraft. Considering pilots have more authority over how much fuel they are going to burn than you might think, the lack of knowledge of pilots who simply do not care is shocking. While pilots are not gods, as they sometimes might want to believe, they certainly can make an impact in how much fuel they are going to burn. Planes are fast and can cover a vast distance while transporting a high volume of passengers. Give me one alternative way of transport that can all do that today. Because there simply is no alternative to flying except maybe for those super short-haul flights. We must look at the data and come up with possible solutions to decrease our impact. While the industry is working towards a more sustainable aviation with ever-improving, more efficient engines, more efficient and shorter standard arrivals and departures, together with free route airspace that allows aircraft to track straight lines from A to B, derated takeoffs and air traffic control doing their best to give pilots shortcuts and continuous idle descents to the initial approach fix. When it comes to the environment, you can always go the extra mile. So what options are available today to make flying a greener way of transport? There is an abundance of data out there collected by universities or even private institutions, sometimes, as you can imagine, with a bit of a bias. For those statistics to work, one has to make a lot of assumptions. For instance, the number of traveled kilometer, the vehicle model, and the occupation rate. All those assumptions will affect the final result. This is a graph published by the European Environment Agency. We could end this video here and conclude that flying an aircraft is the worst thing one can do. But we could take a second look at the data. The number 55 grams of CO2 per passenger per kilometer for an average car assumes a car occupied by 4 people. This assumption is unfortunately not realistic. During the 1980s, the car was occupied by 1.75 people, and that number has decreased to 1.45 according to European Environment Agency. With fewer people, car pollution would be up ×2 or even ×4 if driving alone. At the same time, the 285 grams CO2 per passenger per kilometer for the aircraft considers an occupation rate of 88 people. Pre-COVID, the occupation rate was up 83%. Let's take American Airlines as an example, one of the biggest carriers with over 931 aircraft. It has, throughout its whole fleet, an average of 183 seats per aircraft. Yes, I really did the math. If we are being conservative and estimate a 75% occupation rate, we still have around 130 seats filled, and that is a 156% more than is assumed in the statistic. Let's compare the corrected numbers and values for a second. The 55 grams for an average car becomes 147 grams, assuming a 1.5 occupation rate. And the 285 grams of CO2 for a plane becomes 182 grams and can get as low as 165 grams, assuming a 83% occupation rate. Mind you, all those numbers are actually pretty inaccurate, as the values used do not represent the infrastructure needed, like roads and the motorways or airports in the case of aircraft. Once those statistics take into account fully electric vehicles, it gets even more confusing as those vehicles do not have any direct CO2 emitting to the atmosphere. The mining of the cobalt needed for the batteries and the disposal of the batteries involving melting down the batteries and burning off plastic separators to extract the coveted metals, and of course the kind of electricity the EV is charged with, still play a huge roles in emitting CO2. Remember that over 40% of energy-related carbon dioxide emissions are due to the burning of fossil fuels for electricity generation. While we are getting slightly off topic here, it is important to know how those kind of statistics are produced and what factors and numbers they're considering. Just bear in mind that all those numbers are derived from many different assumptions. Like in every industry, researchers and specialists are trying to cut fuel consumptions, overall costs and emissions. Although emissions most of the time is only a side product of those above. Airlines are not buying new aircraft because they have gotten greener, they are buying new aircraft because they use less fuel. Manufacturers are investing in new technologies like hydrogen or e-power because they expect a demand within the next decade and want to be the first ones to sell planes. Aircraft manufacturers' main objective is to sell planes. If the EU would go ahead and restrict short-haul flights that directly emit CO2, Airbus would have the hydrogen alternative at hand for airlines to purchase. The main reason why billions of dollars are invested in new technology is that the industry is expecting a certain amount of demand within the next decades. That being said, the whole industry is striving to cut costs wherever possible. Fortunate side effect is that trying to cut down costs also cuts down emissions. Engine manufacturers are constantly working on new engine technology. New LEAP engines by CFM have a 15% increase in fuel efficiency over previous generation motors. While that doesn't sound like much, 15% over thousands of aircraft flying every day can make a substantial impact. Composite airframes are saving on weight, wings developed with highly sophisticated computer software to be as efficient as possible at cruising speed. Long story short, even though our main objective is to save money, we are getting greener along the way. If you Google what are the CO2 emissions produced by aviation, you would find a number ranging anywhere from 2 to 5%. Yes, there are numbers out there. Yes, they are derived from scientists who know their stuff, but no, they do not agree. I'm by no means a climate expert, and I can only imagine the complexity that goes into determining the driving factors of climate change. And one reason why they actually vary so drastically is the secondary effects from high altitude flights. This graphic, published by BBC, approximately shows the numbers that we came up with above, with the long-haul flights being only slightly worse than cars and domestic flights being a lot worse than cars. A typical long-haul aircraft burns around 2.9 liters per 100 kilometers per seat. A short-haul aircraft is actually not significantly worse, even given its reduced number of seats. The problem is that a short-haul aircraft has to climb up to 32,000 feet just to cruise there for 40 minutes, and therefore it will burn a lot more liters per seat. Looking only at the fuel consumption of an aircraft per seat, one might think that's actually not too bad, as a car burns way more than that. But the numbers that are really surprising to me are the secondary effects from high altitude flying. New research from Imperial College London suggests that lower altitude flying could greatly decrease the negative effects of flying on the environment. The reason why airlines choose to fly at higher altitudes is to decrease fuel consumption with reduced air density, fly above the weather as turbulent clouds with possible icings are to be avoided, obstacle clearance, and not to forget, the higher you fly, the more options you have in case something goes south. Contrails are human-made clouds that approximately have the same properties as cirrus clouds. They form in air above about 25,000 feet when air is moist and colder than minus 40 degrees Celsius. Like cirrus clouds, they are made up of water vapor. Within a second, the water droplets freeze to make tiny ice crystals that show up visually as contrails. According to the paper, that process causes the atmosphere to trap heat and thus further warming the planet. It is estimated that contrail clouds cover around 0.6% of the globe at any time. Like regular cirrus clouds, contrails have two different effects on climate. They give us shade by reflecting incoming sunlight back into space and also trap heat radiating from the Earth's surface, so causing warming in the air below. Research has concluded that when contrails are present, they raise nighttime temperatures enough to reduce the day-night difference by 3 degrees Celsius. That being said, this research was conducted during the aviation downturn following the terror attacks of 9/11. So really no global data is available at this point. The calculations are complex, and researchers warn it is not clear whether all the warming at cruising altitudes translates to warming at the Earth's surface. But let's say that contrails are actually damaging and we should get rid of them. Contrails are a result of altitude, so lowering the altitude would almost completely eliminate contrails and therefore cut the total impact in half, mitigating the secondary effect. But as mentioned above, choosing a lower altitude comes with many economical and safety critical side effects. Generally speaking, for shorter flights with less time spent on cruise, a turboprop is more efficient. For short to medium haul flights, the turbofan is the way to go. Lowering the altitude on short-haul flights might actually be feasible, as the cruise portion of the flight does not consume the majority of trip fuel. The takeoff and climb to the top of the climb is much more significant. So when turboprops are greener and more efficient than turbofans on short-haul routes, where are all the turboprops? When you look at the traffic at a European airport, the majority of aircraft are either A320s or 737s. To be honest with you, airlines do not really care too much about those numbers. Fuel does only account for approximately 17.7% of the overall expenses, with labor being the biggest piece of the pie with 32.3%. When an airline is acquiring a new aircraft, they have to look at the cost benefit. For most operators in Europe with a medium to short haul network, it simply does not make sense to buy an aircraft that makes financial sense only on very specific routes. If you take a look at the route network of Ryanair, for example, one of the biggest operators in Europe operating exclusively on Boeing 737s, there is only a handful of airports that may make sense to be operated to in a turboprop aircraft. The fact that the biggest turboprop aircraft are only intended for 74 passengers, while the Boeing 737, Ryanair's main aircraft, is up to 180 seats, is not helping. For every new aircraft that might join a fleet in an airline, a new crew of flight attendants, pilots, technicians, and flight instructors have to be trained for that specific aircraft type, along with a new set of simulators and maintenance facilities. Don't get me wrong, turboprop aircraft definitely have their place in a modern fleet of aircraft. Luxair, an airline operating out of Luxembourg, is operating 11 of their de Havilland Q400. They claim that it has significantly lower CO2 emissions compared to other jets of its kind, which makes it a greener and quieter plane that is unrivaled in terms of performance, technology, and comfort. As we learned earlier today, this is definitely true for short hops around Europe, assuming contrails are as damaging as the actual CO2. Air Corsica, another small airline based on the beautiful Mediterranean island of Corsa, is operating ATRs for short hops to the mainland. When you take a look at the seating capacity of the most successful short and medium haul planes, you come to the realization that it's typically double that of what the biggest turboprop passenger planes can offer. So what we may need are turboprop aircraft capable of transporting 120 to 160 passengers that are more efficient than the turbofan counterparts. Engine manufacturers, along with aircraft makers, will play a huge role in shaping the future of the aviation industry. Heart Aerospace's ES-30, a regional electric airplane, has developed a fully electric aircraft with seats for up to 30 passengers. Air Canada, United Airlines and Mesa Airlines ordered the all-new Sweden-made fully electric plane to add to their fleet, the first electric aircraft. The range is very limited to only 124 miles, but it can be extended to 500 miles with a fuel-powered hybrid solution. It has a lithium-ion battery weighing more than 5 tons. Regardless if you need the whole capacity or not, that weight will be with you. That being said, there will hardly be any flights shorter than the published 124 miles range. Smaller general aviation planes for training, sightseeing and private flying might soon benefit from the technology, as maintenance costs will decrease with fewer moving parts, and flight times up to 2 hours are in most cases just fine. Pipistrel aircraft in Slovenia are able to fly traffic patterns for 1 hour without a problem, perfect for training flight students. The Silent 2 Electro, an ultralight registered sailplane, can sustain itself in the air for up to 1 hour with relatively small batteries. With sailplanes, the benefit of the electric powertrain outweigh the disadvantages. They are quieter, easier to maintain, and more reliable. But for profit-orientated people or cargo-carrying commercial aviation, the way to energy density is just not there yet to completely replace fossil fuel. I'm not saying that there is no market for a short-haul aircraft with a 200-kilometer range and a capacity of 30 people at a time where European leaders are thinking about banning short-haul flights all along, and a time when our power grid has been maxed out for years, every day fearing about a nationwide blackout. I'm saying with current battery technology, electric aircraft makes sense on a very finite amount of routes. I'm excited to see companies working on alternative ways of propelling a plane through the air. Although given the weight of the battery and the very limited range, the way you can operate the aircraft is very restrictive. As battery technology improves, or maybe even a completely new way of storing electricity will become reality, things will look a lot different and electric planes could be operated on a variety of different routes. Airbus is heading a completely different route. Although still in development, with the first zero-emission hydrogen aircraft ready by 2035, they promise to have a longer range and a more typical passenger capacity for its class. 3 different concept aircraft categories are proposed. The first one as a traditional jet engine style aircraft similar to an A320, the second one as a turboprop style aircraft similar to an ATR or Dash aircraft, and the last one as the most radical aircraft featuring an all-wing design or blended wing body, BWB as they call it. In the conventional aircraft designs, hydrogen is stored behind the rear bulkhead. Due to its low volumetric energy density, it needs a lot of space to store the energy required. When you take a closer look at the aircraft, you see that the passenger cabin is a lot smaller than its kerosene-powered counterparts. But space is not the only problem with hydrogen. The energy density at ambient temperatures is not suitable for aviation. So you have 2 options. It can either be pressurized up to 700 bars to reach an energy density of 7 times lower than jet fuel, or it can be cooled down to minus 253 degrees. Cooled hydrogen reaches an energy density 4 times lower than jet fuel, which is obviously better. The energy required to compress or cool the hydrogen is immense. If you take electricity to generate hydrogen to then power an electric motor, the efficiency is at about 25 to 30%. So adding to the energy crisis, you would now produce hydrogen needing massive amounts of electricity. To reduce the size of the tanks, liquid hydrogen is used, requiring a cryogenic fuel tank. Cryogenic fuels are fuels needed to be stored at extremely low temperatures. As cylindrical tanks are used, they have to be stored in the fuselage of the aircraft, resulting in longer and a possible wider fuselage. Hydrogen's high specific energy means it would need less fuel weight for the same range, ignoring the added weight and volume of the tanks. The fuel fraction for airlines today is around 26 to 45%, meaning in long-haul aircraft up to 45% of the weight of the aircraft is fuel. And this could be reduced to 9 to 16% with hydrogen fuel. Hydrogen would require a completely new infrastructure at airports and hydrogen production facility, meaning more wind turbines, solar panels, and maybe even nuclear power plants to cope with the immense electricity output needed to produce hydrogen. Looking forward, wind and solar should actually replace fossils and not be used to produce hydrogen. Either with battery-powered aircraft or hydrogen-powered aircraft, you would need heaps of electricity. The good thing about hydrogen is that energy can be stored in big tanks, similar in appearance to kerosene tanks used today. Storing electricity for cloudy days, well, you probably know how hard that is. Both technologies require a huge amount of energy demand. we are hardly able to cope with our current electrical demand. So before considering scaling up either hydrogen or electric powered aircraft, we have to invest in power plants. Wind turbines and solar panels will help, but demand once fossil fuels will almost completely be phased out will be so huge that without gas-fired power plants or similar alternatives, we will most certainly be unable to charge our batteries and produce hydrogen. If the energy to weight ratio of batteries will not substantially change, then batteries will probably be predominantly used for small general aviation and small short-haul airliners. For short and medium-haul airliners, hydrogen could be a good option, although nobody actually talks about the energy it requires to cool down and compress hydrogen. Without compressing or cooling, it is not possible to store hydrogen on an aircraft or on any sort of vehicle simply because of its volume. The first smaller electric general aviation aircraft and small airliners will probably be flying within the next 10 to 20 years. That being said, the majority of aircraft for the next 20 to 30 years will most likely still be powered by fossil fuels. Meanwhile, we could start building the infrastructure required for hydrogen or whatever the future might be. It might be something completely different. To be honest, we have no idea. Airlines could probably do a great deal to reduce the secondary effects with high altitude flying if they choose to operate smaller turboprop aircraft on short-haul routes, which are more efficient at lower altitudes. To really determine the impact the contrail cirrus clouds have on warming and cooling is way too complex to go into. But as we discussed earlier, it's not as easy due to the smaller capacity complexity of a separate aircraft added to a fleet. Long story short, for most airlines, it doesn't make sense financially. Aviation is probably the hardest and most expensive sector to move away from fossils. And frankly speaking, it will not happen in the near future. With the immense power consumption it takes to generate hydrogen and the heavy, low energy density batteries in which basic technology hasn't changed for the last 150 years, alternatives, at least at this point, unfortunately do not really look too promising. With the industrial breakthrough of nuclear fusion, maybe within the next 50 years, we will have an abundance of electrical energy for the next thousands of years. As soon as we have an abundance of electrical energy, or at least more than we need to replace fossils, hydrogen could become a viable option. So what do you think? Will synthetic fuels be replacing fossils in the near future? Hydrogen? Or do you think batteries are the way to go? Write it down in the comments below. I would love to start a discussion on that. Until the next one, stay safe.